The steady-state theory, exploring the universe's origins. Since humanity first began exploring the cosmos, we have sought to understand its origin. The Big Bang theory has become the most widely accepted model for explaining the birth of the universe. However, during the 20th century, an alternative hypothesis emerged, the steady-state theory. This theory presented a bold and revolutionary idea, challenging the notion of a universe with a definitive starting point. According to this model, the universe had no beginning and will have no end, remaining unchanged even as it expands. But how does this theory work? What evidence supports it? And why was it ultimately rejected by most of the scientific community? The steady-state theory was introduced in the 1940s as an alternative to the Big Bang model. It was proposed by three British physicists, Fred Hoyle, Hermann Bondi, and Thomas Gold. Their goal was to answer a fundamental question. If the universe is expanding, why does it look the same over time? The steady-state model suggests that the universe has always existed and always will. As galaxies move away from each other due to cosmic expansion, new matter is continuously created in space, filling the gaps left by receding galaxies. This continuous creation of matter would maintain the universe's overall density, ensuring that it remains roughly the same at all times. Unlike the Big Bang, which describes an evolving universe where temperature, density, and structure change over time, the steady-state model argues that the universe remains unchanged on a large scale, regardless of when we observe it. For Hoyle and his colleagues, this was a more elegant and natural explanation, as it avoided the philosophical dilemma of an absolute beginning. One of the first arguments in favor of this theory was the observation of the universe's expansion. Just like the Big Bang model, steady-state proponents acknowledged that galaxies were moving apart, but they interpreted this phenomenon differently. To them, expansion did not indicate an explosive beginning, but rather a continuous equilibrium, where new matter constantly emerged to sustain the cosmos. Furthermore, the theory seemed to solve the horizon problem. In the Big Bang model, the universe has a finite age, meaning there is a limit to what we can observe. However, in the steady-state model, the universe has always existed and always will, implying that its large-scale appearance should remain constant over time. Despite its appeal, the steady-state theory faced major challenges as new discoveries emerged. One of the biggest blows came in 1965, when Arno Penzias and Robert Wilson detected the cosmic microwave background radiation. This faint radiation, observed in all directions across the sky, was quickly identified as a relic of the Big Bang, a leftover from the early universe. The steady-state model did not predict this radiation, making it a major problem for the theory. Another issue was the discovery that the early universe was different from the present one. In the 1950s and 1960s, astronomers began detecting quasars, extremely bright, distant objects that appear in large numbers only in the early universe. If the universe were truly in a steady state, we would expect to see quasars evenly distributed throughout time. However, observations showed that they were far more common in the distant past, suggesting that the universe has evolved over time, just as the Big Bang model predicts. Additionally, studies on the abundance of chemical elements also favored the Big Bang. The theory predicts that in the first few minutes after the Great Expansion, hydrogen and helium were formed in precise quantities. Observations confirm that the proportions of these elements in the universe match the predictions of the Big Bang model, whereas the steady-state theory lacks a convincing explanation for these observations. As a result of these findings, the steady-state theory lost support and was eventually abandoned by most scientists. However, Fred Hoyle and a few proponents of the model attempted to modify it to fit the new discoveries. Some later versions suggested that the universe might undergo cycles of matter creation and destruction within a broader framework, but these ideas never gained significant acceptance. Today, the Big Bang model is widely considered the best explanation for the universe's origin, but the steady-state theory played a crucial role in the history of cosmology. It was one of the first attempts to create an alternative model for an expanding universe. Additionally, it helped challenge and refine the Big Bang theory by pushing scientists to seek more evidence and improve our understanding of the cosmos. A fundamental question still remains. Did the universe truly have a beginning, or could there be an alternative model we have yet to discover? Could future scientific discoveries reshape our understanding of the cosmos? And what do you think? Do you believe the universe had an absolute beginning, or is there something eternal and continuous? Share your thoughts in the comments and join us on this journey to explore the theory of everything.